Okay. Okay. So in this question, a long straight wire carrying a current of 1 ampere is placed horizontally in a uniform magnetic field 1 into 10 to the power of minus 5 Tesla, pointing vertically upwards. Find the magnitude of the resultant magnetic field at the points P and Q, both situated at a distance of 2 centimeters from the wire in the same horizontal plane. So before doing this question, I would like to review some important uh, aspects related with a long straight wire. If it is carrying a long straight wire, suppose if a long straight wire, if it is carrying a current I, so using Ampere circuitry law, we already proved that. Suppose if I just want to find the magnetic field due to a long straight conductor carrying current I, the equation for magnetic field is equal to mu 0 into I divided by 2 pi R. So V mu 0 is coefficient of permeability and I is the current and R is the distance from this axis of this conductor to this respective point, and 2 pi is the constant, correct? And how we will get the direction, because magnetic field is actually a vector quantity, and this is my magnitude, and how we will find the direction of this magnetic field. So we have to keep our conductor, okay, we have to keep our conductor in our right hand. In that case, the thumb points if we are placing the conductor in such a way that the direction of the current, okay, so we will place this conductor in such a way that thumb points in the direction of the current. In that case, the curl of the finger will point the magnetic field. So these two aspects will help us to solve this question. How? In this question, it is given that the magnetic field are pointing outward. That means this beautiful conductor is placed in an external magnetic field. All these magnetic field lines are, vertically coming outwards. So to represent that in a 2D stuff, I have some limitations. So these are my vertical lines that is coming out perpendicularly, that is coming out from this ball. So here I am placing this, this conductor. So this conductor is carrying a current I. So this is a point P and this is point Q, correct? So I just want to find the magnetic field, because already a vertical magnetic field is there in our P. The magnitude is also given in our question and its direction is also given. So if I'm placing this conductor in our right hand, and if we are keeping in such a way that the thumb points in the direction of the current, the curl of our finger indicates the direction of the magnetic field. So the magnetic field due to a current passing through this conductor at this particular point P will be coming upwards. Okay, so we will write it. We'll write here the magnetic field. The magnetic field due to current passing through the conductor at P is, the magnitude is equal to, because it is the first of all I will explain, I will write the magnitude. So the magnitude is from here, it is 2 centimeters away. Therefore, the distance R is equal to 2 centimeters. So the first I'll write the equation mu 0 I divided by 2 pi R. So we know the value of mu 0, that is 4 pi into 10 to the power of minus 7 into current is, it is also given in our question. The current is 1 ampere current. divided by 2 pi into, what about the radius or the distance? The distance is actually 2 centimeter. So that is 2 into 10 to the power of minus 2 meter. And current is 1 ampere, right? So 2 into 10 to the power of minus 2. If I'm cancelling this stuff, so this 4 pi got cancelled. It eventually becomes 10 to the power of minus 5 Tesla. What about the direction? Coming outwards, vertically. Now, therefore, coming vertically outwards. So therefore, the net magnetic field at P is equal to, one is going in this fashion, because that is our external magnetic field. Again, one more magnetic field is coming in this fashion. So this will be added up. This will be added up. Okay. So what is the magnetic field? The net magnetic field at P. The net magnetic field at P, that is equal to the external magnetic field plus the induced magnetic field. Not induced. This is actually the magnetic field due to the current carrying in the conductor. So the external magnetic field that is placed in the external magnetic field of 1 into 10 to the power of minus 5. So 1 into 10 to the power of minus 5 plus 10 to the power of minus 5, because this is the magnetic field due to the current carrying conductor. So that is 2 into 10 to the power of minus 5 Tesla. Now, coming to the point Q. At Q, the magnetic field due to current flow in the conductor. The distance is also 2 centimeters. So you can see that this is also 2 centimeters away. So the same equation will apply here. So that is 4 pi into 10 to the power of minus 7 into current 1 ampere into 2 into pi into 2 into 10 to the power of minus 2. So we'll get again 10 to the power of minus 5. So what about the direction? So if we are keeping our this thing or conductor in our right hand, current is pointing towards, or the thumb is pointing towards the direction of the current, and you can see that once it reaches to this Q, the magnetic field lines are going into this, into the plane, or it is acting in other ways, it is downwards. So at Q, the external magnetic field is acting upwards, that is 10 to the power of minus 5, and the magnetic field due to this conductor, that is going downwards, that is also 10 to the power of minus 4. Therefore, net B at Q is equal to 10 to the power of minus 4. We have to add by conserving it with the direction. So that is equal to 0 Tesla. So that's the idea about this question. It is not so tricky, but we have to understand this question very clearly. Then only we can answer this question. So here we have to remember this formula. Okay. Otherwise, we have to use Ampere's circuitry law to prove this equation. Then we can do this question. Okay. Thank you.